Right, so the first two questions is about definitions again. So this one, they ask you what is meant by radian. It's asking you to define 1 radian, which is actually a unit. So this one I mentioned to you guys before, it is just the angle subtended at the center of a circle where the arc length is equal to the radius of the circle. Okay, so this one is very simple. And then the next one, this one is a bit different. They told you, why is it that 1 complete revolution is equivalent to an angular displacement of 2 pi radians? Why is it that when you go through 1 full circle like this one full circle is equivalent to 2 pi radian? Okay, so there was a derivation on the first page of your notes which I mentioned to you before. If you know the angular displacement is theta, or rather angle in radians, is your arc length over your radius, we know that for 1 complete circle, your arc length is actually the full circumference of your circle. Okay, for 1 complete circle, your arc length is actually the circumference of your circle, which is 2 pi r. So you sub it inside the equation that you have for angular displacement or angle in radians. This one will be 2 pi r divided by r. Eventually they cancel off, giving you 2 pi radians itself. So the answer was basically this. Theta is s over r. For 1 complete revolution, s will be 2 pi r. 1 complete is basically the circumference of your circle. So sub everything in, you eventually get this. Okay, so this is one part. Now B is the one that is the difficult one. Usually for standalone circular motion questions, they are not as complicated as this. This is the rare exception. Okay, most of the time in your circular motion questions, they are pretty straightforward. It's only this one that is a bit complicated. All right, so let's have a look at this. Okay, now here they tell you that you have an elastic cord that has an unextended length of 13 centimeter. One end of the cord is attached to a fixed point C. A small weight of mass, of weight 5 Newton is hung from the free end of the cord. The cord then extends to a length of 14.8 centimeter. Okay, now one key thing to recognize here is that they mentioned that this is an elastic cord. Okay, meaning to say it can stretch. So when it can stretch, it actually behaves like a spring. Okay, if you apply a load onto it, the cord will extend under the load. So the subsequent description actually is telling you about that. They originally tell you that the unextended length was 13 centimeter. This one is when there is no load. But then after that, when they attach a weight of 5 Newton, a load is attached now to one end of the cord. The cord is actually now extended to a length of 14.8 centimeter. So this one is with load. Okay, so for now, just understand that your cord here is able to extend. It's actually behaving like a spring. Okay, we will make use of this information towards the last part of your question. Now, the later part of the question mentioned this. The cord and mass are now made to rotate at constant angular speed omega in a vertical plane about point C. When the cord is vertical and above C, its length is the unextended length of 13 centimeter. All right. So one thing to note here is that in the previous lesson, I mentioned to you when something moves in a vertical circle, I mentioned that their speed generally will not be the same. The speed at the bottom will usually be higher than the one at the top. But here, they've actually specifically highlighted to you, you actually have constant angular speed when you're trying to swing the cord in a vertical circle. All right, so this one, they've already specifically mentioned to you, you are moving with constant angular speed, or rather you're moving with constant speed. Okay, now when your cord is vertical and above C, the length is the unextended length of 13 centimeter as shown in figure 1.2. If you look at the next part of the question, sorry, next page, this is the diagram showing you what's happening now. The figure 1.2 is showing you the cord when it's at the top position, sorry, when the cord is vertical and the mass is at the top. Figure 1.3 is showing you the chord vertical, but the mass is at the bottom. All right. Now, part 1 show that the angular speed omega of the chord and the mass is 8.7 radians per second. Okay. So in your case, it's actually up to this point here, they've actually only been describing this diagram here, where they tell you that the chord is vertical and mass is above the center of the circle, right? So it's better to analyze on this part only. All right. So you look at the diagram where I tell you this is the center of the circle, and then your chord is like this with your mass here. At the top of your circle, you can say that there is the weight acting on the mass. There's also the tension due to the chord acting on the mass. So this one here, my centripetal force is W plus T, which in turn will give me mr omega square W plus T. I already know that my centripetal acceleration is directed towards the center of the circle. So both these forces are in the same direction, therefore it is positive. Okay. Now, one thing to note here is this. Just now I mentioned to you that your chord is behaving like a spring, right? So your chord behaves like a spring. Just now one of the things I mentioned was that your chord behaves like a spring. Okay. So from here, if you know that just now they told you that your length of your chord is the unextended length of 13 centimeter, this one will actually tell you that tension is 0. Okay. Because the chord behaves like a spring, at the original unextended length, there is no force. Therefore, T is 0. Okay. Because if you say something behaves like a spring, we know that F is equals to Kx. This one is Hooke's law. So from here, F is actually proportional to X, whereas K is your spring constant, obviously. So if K is a constant, force will be directly proportional to your extension. All right. So if you're at the unextended length, that means your X is 0. Therefore, F is 0. Okay. So in your case, your F here is actually your tension in your chord, which will also be exerted onto your mass. All right. So here, that would mean that your original equation will now become this, no? mr omega square equals to W only. All right. So your full working is the one that is written over here. Right. At the top of the circle, W plus T is equals to mr omega square. Since your chord is at the unextended length, T is 0. And then your equation becomes W equals to mr omega square. W is just mg. Then you have mr omega square. The m's will cancel off, giving you 9.81 equals to 0.13 omega squared. Then omega is 8.69 radians per second, and then you will get 8.7 radians per second. All right, this is shown. Okay, so this is all right. Most of the examples you've done so far that involves a mass tied to a string, the string is not extensible. It cannot extend. But this current question that you're doing, the chord is actually extendable. It can actually extend with load like a spring. All right. So that's the one thing about this question that is a bit different than the rest that you've done so far. Okay, so this one is okay. Then after that, we'll move on to part 2. Okay, now for part 2, they tell you that the chord and the mass. Let me get rid of this. For part 2, they tell you that the chord and the mass rotate so that the chord is now vertically below C below the center of the circle, as shown in figure 1.3. Calculate the length L of the chord, assuming that it obeys Hooke's law. Okay. So this time they actually ask you to consider the case at the bottom of your circle. So you're considering the bottom of your circle. If I tell you that this one is the center of your circle, this one is your chord, and this one is your mass, you still have weight W acting down on your mass, but then your tension T would be upwards right now. Okay, so your centripetal acceleration is towards the center of the circle. W is opposite to your AC. This is negative. T is in the same direction as your AC, your centripetal acceleration. So this is positive. Okay. Then from here, you just make use of the equation for centripetal force. Centripetal force here would be T minus W, which in turn would be mR omega square T minus W. Okay. Now I want to use omega here rather than mv squared over r because I already found out omega here. And you already know that omega is constant throughout your motion. So I want to use specifically omega. All right. Now, from here, you will need to start thinking about a few things. They are asking you to find length L. As it is right now, this expression does not have length L. You have to kind of change one of the expression inside here such that it has length L inside. Okay. Now, remember just now I told you that your chord behaves like a spring. So, and here they already told you it obeys Hooke's law. So in your case, if you know that your chord behaves like a spring, you apply Hooke's law to the chord, tension is equals to K times your extension. All right. But extension itself can be rewritten as your length L, final length L minus your original length. Let's just say your original length is L naught lah. Okay, say L naught is your 13 centimeter. The question already told you your unextended length is 13 centimeter. So if you know that your chord behaves like a spring, T can be represented as T equals to Kx, where K is your spring constant, and then your extension is basically your final length L here minus your original length. Okay, but then after that, you will also have another separate issue to deal with. You do not know what is K in the first place. You know L naught as 13. L is what you want to find, but K is also something that you do not know. So this one, you actually have to backtrack a little to what you actually read in the first part of the question. Now, in the first part of the question, they've actually already told you one information where they told you that with no mass, the extended length is 13 centimeter. Okay, this one is no load lah, right? Your length is 13 centimeter. But then after that, when you have a weight of 5 Newton, your chord extends to a length of 14.8 centimeter. This is with load. Okay. Now, if I wanted to find specifically the spring constant from this information, you can find out the spring constant. You can actually just say that T is equals to Kx. Maybe I better just write at the top, at the side here. T is equals to Kx. In your case, your T, or rather your force exerted is 5. K is what you want to find. Your extension here is 14.8 minus 13 multiplied with 10 power minus 2 because you want to change from centimeter to meter. Okay. So all in all, your K is going to be 5 over 0.018. Okay, so you've actually tackled this part where you know what is K and you know what is L naught. The only unknown here is your L. Okay, so you try to sub it back to your original equation. You're going to get mR omega squared equals to K L minus L naught minus W. Then K in turn is your whatever values you have there. All right. So let me just show you the full working. So in your case, you just submit everything that you know, right? In your case, if I submit everything, M will be 5 divided by 9.81. Your radius is actually your L right now. Okay. Your omega is what you found at the top, 8.7 square. Then your K is 5 divided by 0.018 times with L minus with 0.13, 13 centimeter change to meter, and then minus off your weight of 5. Now when you do all this, you try to solve everything. Eventually you get your answer for L as 0.172 meter, which is in turn this one. Okay. Next. So I'll give you guys a minute to digest and copy the workings. All right. Yeah, it's a bit complicated. That's the reason why this question is worth 4 marks. If this kind of question came out nowadays, usually they'll break up your question into a few parts. But in the old days, they tended to lump everything in one single question, and they expect you to figure out all the steps yourself. All right. Yeah, maybe I better just write something else. This one is your R, but it's also your length M. Okay. That's why I can say this one is L. Okay. So that should be it. Okay, right. So with this, we are done with circular motion already. We've gone through all the questions on circular motion that are standalone. All right. Subsequent questions that you see on circular motion after this will usually be combined with another chapter called gravitational field, which is the chapter I'll be going through next. All right.